Okay, so what I want to talk about this morning, or what I want to begin talking about this morning, is this really important idea of likelihood. And I want to contrast a likelihood function with a probability distribution and probability density function. And we'll begin by comparing likelihood function with a probability distribution. And we'll do that using the binomial. And this is actually the correct thing as opposed to all the typos that are in your notes. And I'm going to do this for an imaginary scenario in which we're interested in their sex ratio in some sort of department. And we went out and sampled, and we found that we had 22 females and 8 males. And we're wondering about, is there an equal number of males and females in that population? So one thing we can do is use the binomial distribution right here, and we can create a probability distribution. And here we've got our probability distribution. And we got some data. We've got n is equal to 30. That's the size of our sample. We've got pi is equal to 0.5. And this is going to be our null hypothesis that there are equal numbers of males and females in the population. And then we're going to have our y variable that's going to go from 0 to 30. And 0 to 30, that's what's going to go on the x-axis. And on the y-axis, we have the probability distribution, and it's calculated like this. So this is our probability. Now on the other side, what we're going to have here is likelihood. And we can think of likelihood in some ways as just being a flipped probability. So now we're going to have, as before, n is equal to 30. That's the same. But now pi, instead of being a constant at 0.5, pi is going to go from 0 to 1. So on the y-axis, we've got pi, the probability, the proportion of females in the population going from 0 to 1. And then we've got the data, the number of females being held constant at 22 as opposed to varying from 0 to 30. We've still got on the y-axis, p at y, this thing right here. So some differences between probability and likelihood. This thing here is a true probability distribution. These numbers on the y-axis, they actually have meaning. So if we think about the value here at 10, and it comes across here and you get 0.028, what does that mean? Well, that means if you were to repeat this experiment an infinite number of times with a sample size of 30, if the null hypothesis was true that it was equal to 0.5, then 2.8% of the time, your samples of 30 individuals would give you 10 females. What you've got in this particular situation is not a probability distribution. It's not probabilities. These are not probabilities because the area under the curve does not equal 1. So the interpretation of I should draw it here. The interpretation of these numbers here is not so obvious. And that's why we use different terminology. We call this a probability. We call this a likelihood, in spite of the fact that on both axes that we've got the same thing. So it's another thing that's worth pointing out is that these plots, this one and this one, look really quite different. One of the reasons is that here, our dependent variable is discrete. So we get discrete values in terms of our counts. So you get, in this case, a histogram. Whereas in this case, what's on the y-axis, our dependent variable, is its value of pi, which is continuous, everything between 0 and 1, which is what gives you the smooth curve. So what I've done so far is try to make a distinction between a probability distribution here and a likelihood function here. Now, what do we have here? This is our normal distribution. This is a probability density function. So in the same sense that we went from a probability distribution to a likelihood function, could we go from a probability density to a likelihood function? Yes, we could. Well, we're not going to because it's really nasty, in part because the normal distribution has two parameters, the mean as well as the standard deviation. So now we can think about what sort of inferences might we be able to draw from a probability distribution versus a likelihood function. So let's come back to our binomial distribution and think about the things we could do. We could do null hypothesis statistical testing based on this distribution. If our null hypothesis was that pi was equal to 0.5 and we observed 22 females out of a sample size of 30, you come down here and you see the probability of 22 or more females is only equal to 0.0261, and that would lead us to reject our null hypothesis. Conceptually, we could also do a confidence interval. However, calculating confidence intervals based on binomial distributions is far more difficult than calculating confidence intervals on a normal distribution, so we're not going to do that. Okay, so those are the kind of inferences you can draw based on a probability distribution. What sort of inferences can you draw based on a likelihood function, on this particular likelihood function here? Well, one of the things we can do, and you'll see this a lot in 582, 585, and 586, is what's known as a maximum likelihood estimator. So we could ask ourselves, if we sampled 30 people and found 22 females, what's the best guess about the proportion of females in that population? Well, simple math is going to tell you it's going to be 22 over 30, which is 0.733. But there's an alternative way we could have arrived at that answer. An alternative way to have gotten that answer was have constructed our likelihood function and then found when the likelihood function was maximum, and that would also have given us 0.733. Now, obviously, in a case like this, you're just going to do this. You never construct and find the maximizing value for a likelihood function. The thing is, however, when you actually do real work, like you're going to do for your thesis, maximum likelihood estimation is going to be very important. The other thing you can do in order to draw inferences is to look at relative likelihoods. So consider what we have shown here. This value here and this value here implies that if pi was equal to 0.733, then the likelihood was equal to 0.1630. On the other hand, if pi was equal to 0.5, if there were equal numbers of males in the female population, the likelihood, instead of being 0.1630, would be equal to 0.00545. You take the ratio of these two numbers, and that gives you a value of approximately 30. So what that's telling you is that the probability of observing the particular data, if the pi value was 0.733, is 30 times more likely than getting 22 females had the true underlying proportion been 0.55. You don't actually do null hypothesis statistical testing on this. However, you can use results like this, the relative likelihoods, to draw the inference that, hey, relative to equality, that a disproportionate number of females is the more likely. Next thing I want to talk about is log likelihoods. So here's the likelihood function once more. Right here, there's our likelihood function. And in practice, instead of doing the likelihood function, what we oftentimes do is take the logarithm of the likelihood function. So it gives us a very different shaped curve. But if we think about where the likelihood is maximized, it's 0.733 in both instances. So as it turns out, that when it comes time to use something like a maximum likelihood estimator, you don't just draw some sort of pretty line and eyeball it. There's two ways that we normally arrive at our maximum likelihood estimation. One is involving calculus. So we actually find the function, find the mathematical function here, get the first derivative, set that to 0, and find the maximizing value. The other way is just brute force numerical methods. Either way, doesn't matter which way we use, log likelihoods are more often used than likelihoods. So when you go into 582 and 585, you're going to use log likelihoods as opposed to likelihoods. Now, what I'm going to